Okay, so we're going to look at something that's relates to what we've been talking about. We're going to talk about projectile motion. So we're going to talk about motion in 2 dimensions. I'm trying to make this as simple as I can for you. We'll do some math problems on a couple of the following videos. So what is a projectile? Well, projectile is anything we drop, throw straight up in the air, or even throw at an angle, okay? And the key to being a projectile is that gravity. My pen is not working. Is that gravity is what's doing all the work on the object. So we know that acceleration somewhere is going to deal with, on Earth with negative 9.8 somewhere, okay? So now let's take a look. If we had a cannon and we just shot a cannonball out, if there wasn't gravity, it would take off in a straight line. Now we know in reality that it does go this way, but it also, because of gravity, drops, and that's when we see this parabolic track. Okay, so with gravity, what happens is it pulls it downward. Okay, now we keep going in the horizontal direction. We keep going in the X direction, but in the Y, we drop. Okay, so we drop in the Y, but our X is still going on. We're still going out, even though we're also going down at the same time. So the first type of projectile is a horizontally launched one, and that's the first one we're going to look at mathematically also. But when we go down, you can see the distance between each succeeding second. We're increasing the distance, which means we're accelerating. And again, that's because of gravity. Now, in the X, if you look, our distances are constant. Okay, which means as we go in the X, we have a constant velocity. So as we go in the Y, we accelerate in the X. Our acceleration is constant. And again, you can see there's the vertical path, right? And then you got the horizontal and you got the vertical path. But then you can see the actual path here, okay? And they kind of work together to do this. So now if we launch at an angle in regular, I'll give you some equations to use if you ever run into it. But your assignment will not have any angles, but of course dual credit you will. In the absence of gravity, in the absence of gravity, the cannonball will follow a straight line path and it would just continue to rise up. But in reality, as soon as it leaves the cannon, gravity starts to act on it and will pull it down. And again, this is what we expect to see, even though this is what would happen without gravity. So now let's look at our velocities. You can see in the X, our velocity stays constant, even as our object goes down. So in the X, acceleration in the X is always 0. But if you look in the Y, we accelerate, and our acceleration changes from 0 to negative 9.8, negative da-da-da, negative 20, and etc. But we go down negative 9.8 meters per second every second, which means our acceleration in the Y is our negative 9.8. And that's in meters per second squared. So this is what we expect to see, okay? So in the X, no acceleration, constant velocity, but in the Y, our velocity will change. Now at an angle, you'll see something similar in that our X velocity, in this case 73.1 meters per second, is constant all the way through the travel. Now since we launch upward, we do have an initial velocity in the Y that decreases till we get to the very top where we have no Y, right here. Our Y is 0, and then our Y then starts to become negative as we go down and speed up. And again, for the same reason, in the X, our acceleration is 0, so we have constant velocity, but in the Y, it's negative 9.8 meters per second squared, which means we're going to drop 9.8 meters per second with our Y velocity for every second that we travel. Now, displacement. Since we're traveling at a constant velocity in the horizontal, right, we would see a constant change in our displacement. In this case, 20 meters for every second that we travel. But in the Y, right, we see for the first second 4.9 meters, second 19.6, third second 44.1, etc. So as we go down, our distances increase. And again, that's just because we're accelerating. So if we were to go over 20 and down 4.9, we'd be at this circle. If we were to go over another 20 and go down 19.6, we'd be at this circle. Over 20 down 44.1, over 20 down 48 or 78.4, over 20 down 122.5. And that's where these distances go to. So again, in the horizontal, we have a constant rate because our speed is not accelerated. But in the y, our distances will increase based off of our acceleration, again, of negative 9.8. And you see the same thing with launching at an angle. We're going this direction, which will stay constant. So our x direction stays constant, but our y direction will increase like so. Again, that's just because of accelerated motion and gravity. Now, let's say we launch at an angle and we want to know what our y and x velocities are. This is really pertinent to what you're going to do with the dual credit assignment. So let's say we launch something at 50 meters per second. But we want to find what our x velocity is, and we want to find what our y velocity is. And we just use trig. So if I want to find my x velocity, okay, it's equal to my velocity of the projectile times the cosine of my launch angle. In this case, 25. And for my y velocity, it's the object's velocity multiplied by the sine of the angle. And in this case, 43 meters per second. And you'll see this math again, especially dual credit, as we discuss non-horizontal launched projectiles. Now, a couple other equations. I'm going to go over this when we talk about non-horizontal launch, but peak height, which is initial, if we want to find the peak height of our projectile, if we launch at an angle, is we want to take the initial velocity in the y squared, right, times, so the initial velocity y squared, so that would be this, right, and we'd square that, and we'd divide it by 2 times g. On Earth, that'd be 2 times 9.8. Time of flight, same thing. We take 2 times our initial velocity in the y, and we divide it by g, and that will tell us our time of flight, so how long it takes for the object to fly. And lastly, our range equation. This one's most beneficial. It tells us how far in the x we travel if our x is, if we leave and land on the same y level, okay? Which is initial velocity squared times the sine of 2 times our angle divided by g. And again, on Earth, that will be 9.8. But we'll talk about these equations when we do the non-horizontal launched projectiles. So there are example videos. Both groups, regular and dual credit, watch the horizontally launched problems. Dual credit only. Now regular, you can watch it if you choose. Non-horizontally launched.